This presentation is delivered by the Stanford Center for Professional Development.
Okay, so let's get started with today's material. Welcome back to the second lecture. What I want to do today is talk about linear regression, gradient descent, and the normal equations. And I should also say lecture notes have been posted online, and so if some of the math I go over today, I go over rather quickly. If you want to see every equation written out and work through the details more slowly yourself, go to the course homepage and you can download some detailed lecture notes that pretty much describe all the mathematical, technical content I'm going to go over today. Today I'm also going to delve into some amount of linear algebra. And so if you would like to see a refresher on linear algebra, this week's discussion section will be taught by the TAs and will be a refresher on linear algebra. So if some of the linear algebra I talk about today seems to be going by a bit quickly, or if you just want to see some of the things I'm claiming today without proof, if you want to just see some of those things written out in detail, you can come to this week's discussion section. So I actually want to start by showing you a fun video. Remember at the last lecture, the initial lecture, I talked about supervised learning. And supervised learning was this machine learning problem where I said we're going to tell the algorithm what the quote right answer is for for a number of examples, and then we want the algorithm to replicate more of the same. Right? So the example I had at the first lecture was the problem of predicting housing prices, where you may have a training set, and we tell the algorithm what the quote right housing price was for every house in the training set, and then you want the algorithm to learn the relationship between sizes of houses and the prices, and essentially produce more of the quote right answer. So let me play for you a video now. Actually, load the big screen, please. So let me play for you a video now that was from Dean Pomeroy on some work he did at Carnegie Mellon on applying supervised learning to get a car to drive itself. This was his work on a vehicle known as Alvin. It was done about about 15 years ago, and it was excuse me. I think it was a very elegant example of the sorts of things you can get supervised learning algorithms to do. On the video, you hear Dean Pomeroy's voice mention an algorithm called neural networks. We'll say a little bit about that later, but the essential learning algorithm for this is something called gradient descent, which I actually talk about later in today's lecture. Let's watch the video.
Alvin is a system of artificial neural networks that learns to steer by watching a person drive. Alvin is designed to control the NavLab 2, a modified Army Humvee equipped with sensors, computers, and actuators for autonomous navigation experiments. The initial step in configuring Alvin is training a network to steer. During training, a person drives the vehicle while Alvin watches. Once every 2 seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction. This training image is reduced in resolution to 30 by 32 pixels and provided as input to Alvin's 3-layered network.
So 2 comments, right? One is this is supervised learning because it's learning from a human driver, in which a human driver shows that if we're on this segment of the road, I would steer at this angle. If we're on this segment of the road, I would steer at this angle. And so the human provides a number of, quote, correct steering directions to the car, and then it's the job of the car to try to learn to produce more of these, quote, correct steering directions that keeps the car following the road. On the monitor display up here, I'm just going to tell you a little bit about what this display means. So On the upper left, where the mouse pointer is moving, this horizontal line actually shows the human steering direction, and this white bar or this white area here shows that the steering direction chosen by the human driver by moving the steering wheel. So the human is steering a little bit to the left here, indicated by the position of this white region. This second line here, where my mouse is pointing, the second line here is the output of the learning algorithm, and where the learning algorithm currently thinks is the right steering direction. And right now, what you're seeing is the learning algorithm just at the very beginning of training, and so it actually has no idea where to steer, and so its output is sort of a white smear over the entire range of steering directions. And as the algorithm collects more examples and learns over time, you see it start to more confidently choose the steering direction. So let's keep watching the video.
Using the backpropagation learning algorithm, Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random. After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver. This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving. 12 times per second, Alvin digitizes an image and feeds it to its neural networks. Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. The steering direction from the most confident network, in this case the network trained for the one-lane road, is used to control the vehicle. Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises. When its confidence rises, the two-lane network is selected to steer, safely guiding the vehicle into its lane on the two-lane road.
All right, so who thought driving could be that dramatic, right? Can I switch back to the chalkboard, please? I should say, this work was done about 15 years ago, and autonomous driving has come a long way. So many of you will have heard of the David Grand Challenge, where one of my colleagues, Sebastian Froon, led the winning team to drive a car across the desert by itself. So Alvin was, I think, absolutely amazing work for his time, but I should say, autonomous driving has also come a long way since then. But so, what you just saw was an example, again, of supervised learning, and in particular, it was an example of what I call the regression problem, because the vehicle is trying to predict a continuous value variable, so the continuous value steering directions. We call these, we call it a regression problem. And what I want to do today is talk about our first supervised learning algorithm, and it will also be to a regression task. So for the running example that I'm going to use throughout today's lecture, she's going to return to the example of trying to predict housing prices. So here's actually a data set collected by TA Dan Ramage on housing prices in Portland, Oregon. So here's a data set of a number of houses of different sizes, and here are their asking prices in thousands of dollars. So there's 400,000, 32. Okay, and so you can take this data and plot it. Square feet, that's price. And so you may get a data set like that. And the question is, given a data set like this, or given what we call a training set like this, how do you learn to predict the relationship between the size of a house and the price of a house? So I'm actually going to come back and modify this chart a little bit more later. But let me go ahead and introduce some notation which I'll be using actually throughout the rest of this quarter. First piece of notation is I'm going to let the lowercase alphabet m denote the number of training examples. And that just means the number of rows or the number of examples, houses, and prices we have. And in this particular data set, we have we actually happen to have 47 training examples, although I wrote down only 5. Okay, so throughout this quarter, I'm going to use the alphabet M to denote the number of training examples. I'm going to use, the lowercase alphabet X to denote the input variables, which are often also called the features. And so in this case, X would denote the size of a house that we're looking at. I'm going to use Y to denote the quote output variable, which is sometimes also called the target variable. And so one pair x comma y is what comprises one training example. Okay, in other words, one row on the table I drew out just now would be what I call one training example. And the ith training example in other words, the ith row in that table, I'm going to write as xi comma yi. Okay, and so in this notation I'm going to use, this superscript I is not exponentiation. So this is not x to the power of I, y to the power of I. Okay, in this notation, the superscript I in parentheses is just sort of an index into the ith row of my list of training examples. So in supervised learning, this is how. So this is what we're going to do, I guess. We're given a training set, right. And we're going to feed our training set comprising our M training examples, 47 training examples, into a learning algorithm. Okay, and our algorithm then has to output a function that, so that by tradition and for historical reasons, is usually denoted lowercase alphabet h and is called a hypothesis. Don't worry too much about whether the term hypothesis has a deep meaning. It's more of a term that's used for historical reasons. And the hypothesis's job is to sort of take as input, if there's some new house whose price we want to estimate, what a hypothesis does is it takes as input a new living area in square feet, say, and output the estimated price of this house. So the hypothesis H maps from inputs X to outputs Y. So in order to design the learning algorithm, the first thing we have to decide is how we want to represent the hypothesis, right? And just for the purposes of this lecture, for the purposes of our first learning algorithm, I'm going to use a linear representation for the hypothesis. So I'm going to represent my hypothesis as h of x equals theta 0 plus theta 1x, where x here is an input feature, and so that's the size of the house we're considering. And more generally, I'm actually going to come back to this. More generally, for many regression problems, we may have more than one input feature. So for example, if instead of just knowing the size of the houses, if we know also the number of bedrooms in these houses, 3, 2, let's say, then so if our training set also has the second feature of the number of bedrooms in the house, then you may, let's say, x1 denote the size in square feet. Let x subscript 2 denote the number of bedrooms. And then I would write the hypothesis h of x as theta rho plus theta 1x1 plus theta 2x2. Okay? And sometimes when I want to take the hypothesis h and when I want to make its dependence on the thetas explicit, I'll sometimes write this as h subscript theta of x. And so this is the price that my hypothesis predicts a house with features x costs. Okay? So given a new house with features x with a certain size and a certain number of bedrooms, this is going to be the price that my hypothesis predicts this house is going to cost. Lastly, one final piece of notation. So for conciseness, just to write this a bit more compactly, I'm going to take the convention of defining x0 to be equal to 1. And so I can now write h of x to be equal to sum from I equals 1 to 2 of theta I, 0 to 2 of theta I xi. And if you think of theta and x as vectors, then this is just theta transpose x. And the very final piece of notation is I'm also going to let lowercase alphabet n define let lowercase n be the number of features in my learning problem, and so this actually becomes a sum. Let me just write that. A sum from I equals 0 to n, where in this example, if you have two features, n would be equal to 2. Okay. All right. I realized there was a fair amount of notation. And as I proceed through the rest of the lecture today, or in future weeks as well, if someday you're looking at me write a symbol and you're wondering, gee, what was that symbol lowercase n again, or what was that lowercase x again, or whatever, please raise your hand and ask. This is a fair amount of notation. We'll probably all get used to it in a few days, and with standardized notation, it'll make a lot of our descriptions of learning algorithms much easier. Okay, but again, if you see me write some symbol and you don't quite remember what it means, chances are there are others in this class who've forgotten to. So please raise your hand and ask if you're ever wondering what some symbol means. What questions do you have about any of this? Yeah.
You can just a variable. It can be anything.
Let's see.
Rotation
Yeah.
can be anything.
Wait, oh, say it again.
Theta 0, theta 1.
Yes. Right. So, well, let me. Yeah. So, well, this one's going to do next, but the thetas or the theta i's are called the parameters. The thetas are called the parameters of our learning algorithm, and theta 0, theta 1, theta 2 are just real numbers. And then it's the job of a learning algorithm to use the training set to choose or to learn appropriate parameters theta. Okay. Are there other questions? Yeah.
What is T on the big theta?
Oh, transpose. Sorry, right.
Okay.
Oh, yeah. Sorry, right. So just when write theta tx, I meant theta transpose x, so the inner product between two vectors.
Is this like a typical whatever function, hypothesis function, or could we have like higher orders, or could theta actually be a function in itself?
Yeah, all great questions. The answer, so the question was, what is this a typical hypothesis, or can theta be a function of other variables and so on? And the answer is sort of yes. For now, just for this first, learning algorithm we'll talk about, I'm using a linear hypothesis class. A little bit. Actually, later this quarter, we'll talk about much more complicated hypothesis classes. And we'll actually talk about higher order functions as well a little bit later today. Cool. Okay. So, let's talk about the learning problem then. How do we choose the parameters theta so that our hypothesis H will make accurate predictions about housing prices? Right. So, one reasonable thing to do seems to be that we have a training set. So, and just on the training set, our hypothesis will, make some predictions of the housing prices of the prices of the houses in the training set. So one thing we could do is just try to make the predictions of a learning algorithm accurate on the training set at least, right? So given some features X and some correct prices Y, we might want to make, let's say, the squared difference between the prediction of the algorithm and the actual price small. So to choose the parameters theta, let's say we want to minimize over the parameters theta of this sort of squared error between the predicted price and the actual price. And so I'm going to fill this in. We have m training examples. So I'm going to sum from I equals 1 through m of my m training examples of the price predicted on the ith house in my training set minus the actual target variable minus the actual price on the ith training example. And by convention, instead of minimizing this sum of squares differences, I'm just going to put a 1/2 there, which will simplify some of the math we do later. Okay? And so, let me go ahead and define j of theta to be equal to just this thing, 1/2 sum from I equals 1 through m, our number of training examples, of the value predicted by my hypothesis minus the actual value. And so what we'll do, let's say, is minimize as a function of the parameters of theta this quantity j of theta. Okay. I should say, to those of you that have taken linear algebra classes or maybe basic statistics classes, some of you may have seen things like these before and seen it called least squares regression or ordering least squares. Many of you will not have seen this before. I think some of you may have seen it before. But either way, regardless of whether you've seen it before, let's keep going. And just for those of you that have seen it before, I should say, eventually we'll actually show that this algorithm is a special case of a much broader class of algorithms. But let's keep going. We'll get there eventually. So I'm going to talk about a couple of different algorithms for performing that minimization over theta of j of theta. First algorithm I'm going to talk about is a search algorithm where the basic idea is we'll start with some value of my parameter vector theta. Maybe initialize my parameter vector theta to be the vector of all zeros. Excuse me, I have to write that. I sort of write 0 with an arrow on top to denote the vector of all zeros. And then, when we keep changing my parameter vector theta to reduce j of theta a little bit until we hopefully end up at the minimum with respect to theta of j of theta. Okay, so should switch the laptop display, please, and load the big screen. So let me go ahead and show you an animation of this first algorithm for minimizing j of theta, which is an algorithm called gradient descent. So here's the idea. You see on the display a plot, and the axes, so the horizontal axes are theta 0 and theta 1. Right? So you should minimize j of theta, which is represented by the height of this plot. Right? So the surface represents a function j of theta, and the axes of this function, or the inputs of this function, are the parameters theta 0 and theta 1, written down here below. So here's the gradient descent algorithm. I'm going to choose some initial point. It could be, vector of all zeros or some randomly chosen point. And let's say we start from that point denoted by the cross, by the star, by the cross. And now I want you to imagine that this display actually shows a 3D landscape. Imagine it's out in a hilly park or something, and this is the 3D shape of like a hill in some park. So imagine you're actually standing physically at the position of that star, of that cross. And imagine you're going to stand on that hill, right, and look all 360 degrees around you and ask, if I were to take a small step, what would allow me to go downhill the most? Okay, so imagine that this is physically a hill and you're standing there. You want to look around and ask, if I take a small step, what is the direction of steepest descent that would take me downhill as quickly as possible? So the gradient descent algorithm does exactly that. We're going to take a small step in this direction of steepest descent, or in the direction of the gradient it turns out to be. And then you take a small step and you end up at a new point shown up there. And then we keep going. You're now at a new point on this hill, and again you're going to look around you, look all 360 degrees around you, and ask, what is the direction that would take me downhill as quickly as possible? And we want to go downhill as quickly as possible because we want to find the minimum of j of theta. So you do that again, you can take another step. Okay? And you sort of keep going until you end up at a local minimum of this function, j of theta. Okay? One property of gradient descent is that where you end up, in this case we ended up at this point on the lower left-hand corner of this plot. But let's try running gradient descent again from a different position. Also, that was where I started gradient descent just now. Let's rerun gradient descent, but using a slightly different initial starting point. So the point slightly further to the up and further to the right. So it turns out if you run gradient descent from that point, then if you take a steepest descent direction again, that's your first step. And if you keep going, turns out that with a slightly different initial starting point, you can actually end up at a completely different local optimum. Okay? So this is the property of gradient descent. We'll come back to in a second, but so be aware that gradient descent can sometimes depend on where you initialize your parameters, theta 0 and theta 1. But actually, let's switch back to the chalkboard, please. Let's go ahead and work out the math of the gradient descent algorithm. Then we'll come back and revisit this issue of local optima. So here's the gradient descent algorithm. We're going to repeatedly take a step in this direction of steepest descent, and it turns out that you can write that as follows, which is we're going to update the parameters theta as theta I minus the partial derivative with respect to theta I of j of theta. Okay, so this is how we're going to update the I parameter theta I, how we're going to update theta I on each iteration of gradient descent. Just a point of note and notation, I use this colon equals notation to denote sort of setting a variable on the left-hand side to be equal to the variable on the right-hand side. Right? So if I write a colon equals b, then what I'm saying is this is part of a computer program, or this is part of an algorithm where we take the value of b, or the value on the right-hand side, and use that to overwrite the value on the left-hand side. In contrast, if I write a equals b, then this is an assertion of truth. Well, I'm claiming that the value of a is equal to the value of b. Okay, and so whereas this is a computer operation where we overwrite the value of a, if I write a equals b, then I'm sort of asserting that the values of a and b are equal. So let's see. This algorithm sort of makes sense. Well, actually, let's just move on. Let's go ahead and take this algorithm and apply it to our problem. To work out gradient descent, let's take gradient descent and just apply it to our problem. And this being the first somewhat mathematical lecture, I'm going to step through derivations much more slowly and carefully than I will later in this course. We'll just work through the steps of these in much more detail than I will later in this quarter. Let's actually work out what this gradient descent rule is. And I'll do this just for the case of if we have only one training example. Okay. So in this case, we need to work out what the partial derivative with respect to the parameter theta I is of j of theta. If we have only one training example, then j of theta is going to be 1/2 x subscript theta of x minus y squared. Right? So if you have only one training example comprising one pair x comma y, then this is what j of theta is going to be. And so taking derivatives, you have 1/2 something squared, so the 2 comes down, so you have 2 times 1/2 times x subscript theta of x minus y. And then by the chain rule of derivatives, we also need to multiply this by the derivative of what's inside the square. Right? The 2 and the 1/2 cancel, so this leaves h times that is theta 0 x 0 plus dot 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 plus theta n. Okay, and if you look inside this sum, we're taking the partial derivative of this sum with respect to the parameter theta I, but all the terms in this sum except for one do not depend on theta I. Right? The only in this sum, the only term that depends on theta I will be some term here of theta I xi, and so we take the partial derivative with respect to theta I xi, take the partial derivative with respect to theta I of this term theta I xi, and so you get that times xi. Okay? And so this gives us our learning rule, right, of theta I gets updated as theta I minus alpha times that. Okay? this Greek alphabet alpha here is a parameter of the algorithm called the learning rate. And this parameter alpha controls how large a step you take. So if you're standing on the hill, you decided what direction to take a step in. And so this parameter alpha controls how aggressively how large a step you take in this direction of steepest descent. Okay? And so if alpha, and this is a parameter of the algorithm that's often set by hand. If you choose alpha to be too small, then your steepest descent algorithm will take very tiny steps and take a long time to converge. If alpha is too large, then the steepest descent may actually end up overshooting the minimum if you're taking too aggressive a step. Okay, yeah. Say that again?
Isn't there an 1/2 missing somewhere?
Is there a 1/2 missing?
I know it's gradient. Okay.
No. Okay, cool. Thanks. I do make lots of errors in math, so it's good to. Any questions about this? Okay, so questions, right? So let me just wrap this up properly into an algorithm. So over there, I derived the algorithm for if you have just one training example. More generally, for m training examples, gradient descent becomes the following. We're going to repeat until convergence the following step. Okay, theta I gets updated as theta I, and I'm just writing out the appropriate equation for m examples rather than one example. Theta I gets updated as theta I minus alpha times sum from I equals 1 to m. Okay, and I won't bother to show it, but you can go home and verify for yourself that this summation here, this is indeed the partial derivative with respect to theta I of j of theta, where if you use the original definition of j of theta for when you have m training examples. Okay, so let me just go ahead and switch back to the laptop display. Let me just show you what this looks like when you run the algorithm. So it turns out that for the specific problem of linear regression or ordinary least squares, which is what we're doing today, the function j of theta actually does not look like this nasty one that I was showing you just now with multiple local optima. In particular, it turns out for ordinary least squares, the function j of theta is just a quadratic function, and so it'll always have a nice bow-shaped like what you see up here, and it'll only have one global minimum with no other local optima. So when you run gradient descent, here are actually the contours of a function j. So the contours of a bow-shaped function like that are going to be ellipses, and if you run gradient descent on this algorithm, here's what you might get. So let's see, initialize the parameters, so let's say randomly at the position of that cross over there, right? That cross on the upper right. And so after one iteration of gradient descent, as you change in the space of parameters, so that's the result of one step of gradient descent, 2 steps, 3 steps, 4 steps, 5 steps, and so on, and it converges reasonably rapidly to the global minimum of this function j of theta. Okay, and this is a property of least squares, of ordinary least squares regression, with a linear hypothesis clause that the function j of theta has no local optima. This question?
Is alpha changing every time because the step is not?
I see. Yeah. Okay. So it turns out that. Yes, so it turns out this was done with actually did this with a fixed value of alpha, and one of the properties of gradient descent is that as you approach a local minimum, it actually takes smaller and smaller steps, so they'll converge. And the reason is the update is you update theta by subtracting from it, alpha times the gradient. And so as you approach a local minimum, the gradient also goes to 0, right? So and as you approach the local minimum, at the local minimum, the gradient is 0. And as you approach the local minimum, the gradient also gets smaller and smaller. And so gradient descent will automatically take smaller and smaller steps as you approach a local minimum. Does that make sense? And here's the same plot and so here's actually a plot of the housing prices data. So here, let's say you initialize the parameters to the vector of all zeros. And so this blue line at the bottom shows the hypothesis with the parameters at initialization, right? So initially, theta 0 and theta 1 are both 0, and so your hypothesis predicts that all prices are equal to 0. After one iteration of gradient descent, that's the blue line you get. After 2 iterations, 3, 4, 5, and after a few more iterations, it converges, and you've now found the least squares fit to the data. Okay. Cool. Let's switch back to the chalkboard. So are there questions about this? Yeah. Sid?
When we say run an iteration, we mean that we run each sample, all the sample cases once, update the value of the parameters and run it again with the new values?
Yes, right.
And converge means that the value will remain same of the theta I, the parameters will remain roughly the same?
Yeah, so a question of how do you test for convergence, right? And there's different ways of testing for convergence. One is you can look at 2 different iterations and see if theta's changed a lot. And if theta hasn't changed much within 2 iterations, you may say it's sort of more or less converged. Something that's done maybe slightly more often is look at the value of j of theta. And if j of theta, so if the quantity you're trying to minimize is not changing much anymore, then you might be inclined to believe it's converged. So these are sort of standard heuristics or standard rules of thumb that are often used to decide if gradient descent has converged yet. Okay. Yeah.
I may have missed something, but you mentioned that you look at all the different directions, and choose the direction with the lowest gradient descent. So in the one feature example, you basically have 2 directions that you can either, it's like a 2D curve, and you can either go this way or that way.
Yep.
But the math, I didn't quite understand where that comes in. When do you choose whether you go left, whether you go this way or that way, basically?
I see. Okay. So it actually turns out that so the question is if how is gradient descent looking 360 around you and choosing the direction of steepest descent? So it actually turns out, I'm not sure I understood the second part, but it turns out that if you if you stand on the hill and if you it turns out that when you compute the gradient of a function, when you compute the derivative of a function, then it just turns out that that is indeed the direction of steepest descent. But I just want to point out, you would never want to go in the opposite direction because the opposite direction would actually be the direction of steepest ascent, right? So it turns out, maybe the TAs can talk a bit more about this at the section if there's interest. Turns out when you take the derivative of a function, so it turns out to just give you the direction of steepest descent. And so you don't explicitly, look all 360 degrees around you. You sort of just compute the derivative, and that turns out to be the direction of steepest descent. Yeah, maybe the TAs, maybe the TAs can talk a bit more about this on Friday. Okay. Let's see. So let me go ahead and give this algorithm a specific name. So this algorithm here is actually called batch gradient descent. And the term batch isn't a great term, but the term batch refers to the fact that on every step of gradient descent, you're going to look at the entire training set. You're going to, perform a sum over all m training examples. Turns out, so batch gradient descent often works very well. So I use it very often. And it turns out that sometimes if you have a really, really large training set, so imagine that instead of having 47 houses from Portland, Oregon in a training set, if you had, say, the US Census database or something. With US Census size databases, you can often have hundreds of thousands or millions of training examples. So if M is a few million, then if you're running batch gradient descent, then this means that to perform every step of gradient descent, you need to perform a sum from j equals 1 to a million, which is, and that's sort of a lot of training examples for your computer program to have to look at before you can even take one step downhill on the function j of theta. So it turns out that when you have very large training sets, let me write down an alternative algorithm that's called stochastic gradient descent. Sometimes also called incremental gradient descent. But the algorithm is as follows. Again, we'll repeat until convergence. And we'll iterate for j equals 1 to m. And we'll perform one of these sort of gradient descent updates using just the j training example. Oops. Minus. Okay. Oh, and as usual, this is that really you update all the parameters theta. So you perform this update, for all values of I. Right, meaning for I indexes in the parameter vectors, you just perform this update for all of your parameters simultaneously. And the advantage of this algorithm is that in order to start learning, in order to start modifying the parameters, you only need to look at your first training examples. You look at your first training example and perform an update using the derivative of the error with respect to just your first training example, and then you look at your second training example and perform another update, and you sort of keep adapting your parameters much more quickly without needing to take a scan over your entire US Census database before you can even start adapting your parameters. So let's see. For large data sets, stochastic gradient descent is often much faster. And what happens with stochastic gradient descent is that it won't actually converge to the global minimum exactly. But well, if these are the contours of your function, then as you run stochastic gradient descent, you sort of tend to wander around. And you may actually end up going uphill occasionally, but your parameters will sort of tend to wander to the region close to the global minimum, but sort of keep wandering around a little bit near the region of the global minimum. And often that's just fine, right? To have a parameter, that wanders around a little bit the global minimum. And so and in practice, this often works much faster than batch gradient descent, especially if you have a large training set. I'm going to clean a couple of boards. While I do that, why don't you take a look at the equations, and after I'm done cleaning the boards, I'll ask what questions you have. Let's get those. So what questions do you have about all this? Yeah.
So in stochastic gradient descent, is it true that are you just sort of like rearranging the order that you do the computation? Like, so do you just use the first training sample and update all of the theta i's and then step, and then update with the second training example and update all the theta i's and then step? And is that why you get sort of this early?
Yeah, let's see, right. So I'm going to look at my first training example, and then I'm going to take a step, and then I'm going to perform the second gradient descent update using my new parameter vector that has already been modified using my first training example. And then I keep going. Does that make sense? Yeah.
So in each update of all the theta i's, you're only using
one training example.
One training example.
Faster than batch, is it empirical or?
Let's see, it's definitely empirical. I believe there's theory that sort of supports that as well. You know, Zico? Yeah, there's theory that supports that. How clean the statement of the theorem is, I don't remember, but yeah. Yes? Great. Okay, cool. So, in what I've done so far, I've talked about an iterative algorithm for performing this minimization in terms of j of theta. And it turns out that there's another way for the specific problem of least squares regression, of ordinary least squares. Turns out there's another way to perform this minimization of j of theta that allows you to solve for the parameters theta in closed form without needing to run an iterative algorithm. And I don't know, some of you may have seen some of what I'm about to do before in like an undergraduate linear algebra course. And the way it's typically done, so it requires messy orthogonal projections or taking lots of derivatives and writing lots of algebra. What I'd like to do is show you a way to derive the closed form solution of theta in just a few lines of algebra. But to do that, I need to introduce a new notation for matrix derivatives. It turns out that sort of the notation I'm about to define here, just in my own personal work, has turned out to be one of the most useful things that I actually use all the time, to have a notation for how to take derivatives with respect to matrices, so that you can solve for the minimum of j of theta with like a few lines of algebra rather than writing out pages and pages of matrices and derivatives. So then we'll go ahead and define this new notation first, and then we'll go ahead and work out the minimization. Given a function j, since j is a function of a vector parameter theta, right? I'm going to define the derivative or the gradient of j with respect to theta as itself a vector. Okay, and so this is going to be, an n+1 dimensional vector. Remember, theta is an n+1 dimensional vector with indices ranging from 0 to n, and so I'm going to define this derivative to be equal to that. Okay, and so we can actually rewrite the gradient descent algorithm as follows. I guess this is a bash gradient descent, and rewrite gradient descent as updating the parameter vector theta. Notice there's no subscript I now. Updating the parameter vector theta as the previous parameter minus alpha times the gradient. Okay? And so in this equation, all of these quantities, theta and this gradient vector, all of these are n+1 dimensional vectors. Oh, I see, right. I was using the boards out of order, wasn't I? So more generally, if you have a function f that maps from the space of matrices A, excuse me, that maps from, say, the space of n by n matrices to the space of real numbers. So if you have a function, you know, f of a, where a is an n by n matrix. So this is a function that maps from matrices to real numbers. It's a function that takes this input to matrix. Let me define the derivative with respect to f of the matrix A. Right? Now this is taking the gradient of f with respect to its input, which is a matrix. I'm going to define this itself to be a matrix. So the derivative of f with respect to A is itself a matrix, and the matrix contains all the partial derivatives of f with respect to the elements of A. One more definition is if A is a square matrix, so if A is an n by n matrix, number of rows equals number of columns, let me define the trace of A to be equal to the sum of A's diagonal elements. Okay, so this is just sum over I of AII. For those of you that haven't seen this sort of operator notation before, you can think of trace of A as, you know, the trace operator applied to the square matrix A, but it's more commonly written without the parentheses. So I usually write the trace of A like this. And this just means the sum of diagonal elements. So here are some facts about the trace operator and about derivatives. And I'm just going to write these without proof. And you can also TAs to prove some of them at the discussion section, or you can actually go home and verify the proofs of all of these yourself. It turns out that given two matrices, A and B, the trace of the matrix A times B is equal to the trace of BA. Okay, I'm not going to prove this, but you should be able to go home and prove this yourself without too much difficulty. And similarly, the trace of a product of three matrices, so if you can take the matrix at the end and, you know, cyclically permute it to the front. This trace of A times B times C is equal to the trace of CAB. So take the matrix C at the back and move it to the front. And this is also equal to the trace of BCA. We take the matrix B and move it to the front. Okay. Also, suppose you have a function f of A, which is defined as a trace of AB. Okay, so this is, right, the trace is a real number, so the trace of AB is sort of a function that takes its input in matrix A and outputs a real number. So then the derivative with respect to the matrix A of this function of trace AB is going to be B transpose. And this is just another fact that you can prove by yourself by going back and referring to the definitions of traces and matrix derivatives. But I'm not going to prove this. You should really work it out. Okay. And lastly, a couple of easy ones. The trace of A is equal to the trace of A transpose, because the trace is just the sum of diagonal elements. And so if you transpose the matrix, the diagonal elements don't change. And if lowercase a is a real number, then, you know, the trace of a real number is just itself. So think of a real number as a 1 by 1 matrix. So the trace of a 1 by 1 matrix is just whatever, you know, whatever that real number is. Boy. And lastly, this is a somewhat tricky one. The derivative with respect to the matrix A of the trace of ABA transpose C is equal to CAB plus C transpose A B transpose. And I won't prove that either. This is sort of just algebra and work it out yourself. Okay, and so the I guess key equations, the key facts I'm going to use again about traces and matrix derivatives are these 5. 10 minutes, okay. So armed with these things, I'm going to figure out, let's try to come up with a quick derivation for how to minimize j of theta as a function of theta in closed form and without needing to use an iterative algorithm. To work this out, let me define the matrix X. This is called the design matrix. To be a matrix containing all the inputs from my training set. Right? So, X1 was sort of the vector of inputs, the vector of features for my first training example. So I'm going to set X1 to be the first row of this matrix X. Set my second training example's inputs to be the second row, and so on. And I have m training examples, and so that's going to be my design matrix X. Okay, I'm just define this matrix capital X as follows. And so now let me take this matrix X and multiply it by my parameter vector theta. This derivation will just take 2 or 3 steps. So X times theta. Remember how matrix vector multiplications goes, right? You take this vector and you multiply by each of the rows of the matrix. So X times theta is going to be just, X1 transpose theta dot 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 down to Xm transpose theta. And this is, of course, just the predictions of your hypothesis on each of your M training examples. Let me also define the Y vector to be the vector of all the target values Y1 through Ym in my training set. Okay, so Y vector is an M-dimensional vector. So X theta minus Y, containing the math from the previous board, is going to be H of that, right? And now X theta minus Y, this is a vector. This is an M-dimensional vector if I have M training examples. And so I'm actually going to take this vector and take its inner product with itself. Okay, so recall that if Z is a vector, then Z transpose Z is just sum over I Zi squared, right? That's how you take the inner product of a vector with itself. So I'm going to take this vector X theta minus Y and take the inner product of this vector with itself. And so that gives me sum from I equals 1 to m of h of xi minus y squared. Okay, since it's just the sum of, the sum of squares of the elements of this vector. And for the half there, then this is our previous definition of j of theta. Okay? Yeah?
Did you miss the 0th element? Because that's the scalar bias.
Okay, right. So, yeah, I know. I threw a lot of notation at you today. So, m is the number of training examples, and the number of training examples runs from 1 through m, and then is the feature vector that runs from 0 through n. Does that make sense? So, so this is a sum from 1 through m. Is sort of theta transpose x that's equal to sum from j equals 0 through n of theta I x theta j xj. Does that make sense? Okay. So it's sort of the feature vectors that index from 0 through n, where x0 is equal to 1, whereas the training example is actually indexed from 1 through m. Okay. So let me clean a few more boards and take another look at this and make sure it all makes sense. Okay. Yeah.
Bottom line, shouldn't the y inside the parentheses, shouldn't that be
Oh,
y
yes.
to the I?
Thank you. Yes, why? Oh, is that what you meant? No. Oh, okay. Yes, thank you. This should be right. I training example. Anything else? Okay, cool. So, we're actually nearly done with this derivation. We'd like to minimize j of theta with respect to theta. And we've written j of theta fairly compactly using this matrix vector notation. So in order to minimize j of theta with respect to theta, what we're going to do is take the derivative with respect to theta of j of theta and set this to 0 and solve for theta. Okay? So we have derivative with respect to theta of that is equal to, I should mention there'll be some steps here that I'm just going to do fairly quickly without proof. So is it really true that the derivative of half of that is half of the derivative? Can I really exchange the derivative and then 1/2? It turns out the answer is yes, but later on you should go home and look for the lecture notes and make sure that you understand and believe why every step is correct. And I'm going to do things relatively quickly here, and you can work through every step yourself more slowly by referring to lecture notes. Okay? So that's equal to, I'm going to expand out this quadratic function. So this is going to be okay. And this is just sort of taking a quadratic function and expanding it out by multiplying the arguments. And again, work through this step later yourself if you're not quite sure how I did that. So this thing, this vector-vector product, right? This quantity here, this is just j of theta, and so it's just a real number. And the trace of a real number is just itself. Oh, Dan? Oh, thanks, Dan. Cool. Right. So this quantity in parentheses, this is j of theta, and it's just a real number. And so the trace of a real number is just the same real number. And so I can sort of take a trace operator without changing anything. And this is equal to 1/2 derivative with respect to theta of the trace of, by the cyclic permutation property of trace, I can take this theta at the end and move it to the front. So this is going to be trace of theta times theta transpose x transpose x minus derivative with respect to theta of the trace of, and again, I'm going to take that and bring it to the, you know what? Actually, this thing here is also a real number, and the transpose of a real number is just itself, right? So I can take the transpose of a real number without changing anything. So let me go ahead and just take the transpose of this. So a real number transpose itself is just the same real number. So this is minus the trace of, taking the transpose of that gives y transpose x theta, then minus y transpose x theta. Okay? And this last quantity, y transpose y, it doesn't actually depend on theta. So when I take the derivative of this last term with respect to theta, is 0. So just drop that term. And lastly, well, the derivative with respect to theta of the trace of, theta transpose x transpose x. I'm going to use I'm going to use one of the facts I wrote down earlier without proof, right? And I'm going to let this be A. Insert the identity matrix there. So this is AB A transpose C. And using a rule that I've written down previously, that you find in lecture notes, or I guess it's still on one of the boards, but you have previously, this is just equal to x transpose x theta, excuse me. So this is C, A, B, which is just the identity matrix, which you can ignore, plus x transpose x theta, where this is now C transpose A, again, times the identity, which you can ignore, times B transpose. Okay? And the matrix x transpose x is symmetric, so C transpose is equal to C. Similarly, the derivative with respect to theta of the trace of, excuse me, y transpose theta x, this is the derivative with respect to a matrix A of the trace of BA, and this is just x transpose y. Right? This is just B transpose by one of the rules that I wrote down earlier. And so if you plug this back in, we find, therefore, that the derivative, wow, this board's really bad. This is a different one. Oh, well. So if you plug this back into our formula for the derivative of j, you find that the derivative with respect to theta of j of theta is equal to 1/2 x transpose x theta plus x transpose x theta minus x transpose y minus x transpose y, which is just x transpose x theta minus x transpose y. Okay? So we set this to 0, and we get that which is called the normal equations. And we can now solve this equation for theta in closed form as x transpose x theta inverse times x transpose y. And so this gives us a way for solving for the least squares fit to the parameters in closed form without needing to use an iterative algorithm like gradient descent. Okay? And using this sort of matrix vector notation, I think I don't know, it took far fewer. I think we did this whole thing in about 10 minutes, which we couldn't have if I was writing out reams of algebra. Okay. Some of you look a little bit dazed, but guys, this is our first learning algorithm. Aren't you excited? Any quick questions about this before we close for today? Oh.
Just pseudo inverse of x?
Say that again?
What you derived here, wasn't that just a pseudo inverse of x?
What inverse?
Pseudo inverse.
Pseudo inverse?
Pseudo inverse.
Yeah, it turns out that in cases, if x transpose x is not invertible, then you use the pseudo inverse to minimize, to solve this. But it turns out if x transpose x is not invertible, that usually means your features were dependent. It usually means you did something like repeat the same feature twice in your training set. So if this is not invertible, it turns out the minimum is obtained by the pseudo inverse instead of the inverse. If you don't know what I just said, don't worry about it. It usually won't be a problem. Anything else?
On the second board, when we start that derivative, where does the trace come from?
Let me take that offline. I think we're running over. Let's close for today, and if there are other questions, I'll take them offline. Okay. Thanks, guys.